I'd like to begin this chapter in an unusual way. I'm going to read from Romans chapter 8. This is a passage of scripture that precedes one of the most famous verses, Romans 8:28. Beginning with verse 18, Paul speaking, "I consider that our present sufferings are not worth comparing with the glory that will be revealed in us. The creation waits in eager expectation for the sons of God to be revealed. For the creation was subjected to frustration, not by its own choice, but by the will of the one who subjected it, in hope that the creation itself will be liberated from its bondage to decay and brought into the glorious freedom of the children of God." We can talk for hours about this passage of Scripture, but in the context of our present circumstances with the COVID-19 virus, it's interesting to ask, is the COVID-19 virus the result of human sin? And the answer is, it's part of God's creation, and just like bacteria, viruses serve a good purpose. Viruses, for example, help to fight diseases, help to alert the immune system to various issues. This particular virus, I don't know what its proper role is in the environment, but it reminds us that ever since the fall, Adam and Eve's sin, in which we all participated, there are aspects of all of creation that seem to, instead of cooperate with us, they push back. Thorns and thistles, for example, have a good place in God's good creation. But after the fall, in Genesis chapter 3, they start showing up in places where they don't belong. They get in the way of human flourishing. This is one of the consequences of human sin. And it's one of the things that we look forward to when Jesus comes back again, and we find that his creation now, once again, fully cooperates with us as we go about our business of honoring God and praising him in all of the activities that we will have in his creation as a part of our praise. Now, in this chapter, relative to the term entropy, which is a key concept, I have heard some Christians say that entropy, which is things, one way of thinking about it, things wearing out, falling apart, becoming more and more disordered, that entropy did not happen until sin. There was no entropy until Adam and Eve sinned. And I would have to disagree with that position. I think, for example, that even before Adam and Eve sinned, and the rest of us fell with them, that if they were to take a handful of dirt and toss it in the wind, the dirt would become distributed, that things would spread out, that if leaves were to fall off of trees, they would be dispersed and they would spread out. And that's one of the definitions of entropy. It's an entirely different question to think about whether or not Adam and Eve would gradually age and wear out during the period of time before the sin as they worked in the garden and went about God's business. And we might speculate that that was one of the purposes of the tree of life, that before the fall, Adam and Eve could take part of the tree of life, and this is what helped to prevent the ravages of wearing out and aging and having the body become more and more worn and function less and less aptly. That's an interesting speculation. But I think we want to be very careful if you get into conversations about the second law of thermodynamics with people that are talking about it relative to the opening chapters of Genesis. Now, we're going to be going through this chapter very, very quickly and not be able to hit on all the essential points. You might recall from first-year chemistry, which actually covered this chapter pretty well in terms of the nuts and bolts that we want to remember and understand, that while I was talking about the definition of the word spontaneous, I suddenly just yelled, and some of you jumped. And the point was that in science, as is often the case, we have a very different definition of words than how they might ordinarily be used in everyday conversation. The word spontaneous here doesn't mean unexpected. It doesn't mean out of the blue. It doesn't mean on the spur of the moment. Spontaneous simply means a change that occurs in one direction that leads you back to equilibrium. You would spontaneously go to the left or go to the right until you reach an equilibrium or a balance. Sometimes that equilibrium goes all the way to the right, like in an explosion. Eventually you have a complete distribution of all the gas particles that were produced as a result of that explosion or combustion. Notice there's nothing in here about it having to be in a short amount of time. So spontaneous changes can be very, very slow. Think of the rusting process, slow oxidation, or it can be very, very rapid. Think of combustion of the gasoline in a car engine, for example. Now, another point that is important to make is that systems never change spontaneously in a direction that takes them further from equilibrium. For example, if we had a lot of air in a room, and that's always a good thing, you hate it when you don't, we would never expect all of the oxygen that's evenly distributed throughout the room to, for some reason, for some moment, all end up in the upper left-hand corner of the room and not be present in the rest of the room. Gas particles do not naturally distribute themselves going from low concentration to high concentration. It's always the other way around. So spontaneity leads you in the direction of equilibrium. Now, spontaneity not only talks about how particles are going to move, it also talks about how energy is going to move, how heat is going to be transferred. And so when we think of the transfer of heat, for example, if it was cold outside and it was warm inside, you would never expect that some of the heat energy outside, if you open the door, the net flow of that heat would be into the house, making the house warmer. You would always expect heat to go from where you have lots of it to where you don't have as much of it. You would always expect heat to go from where the temperature is higher to where the temperature is lower. That would be the net direction of the heat energy. That would be spontaneous. It would be non-spontaneous to move in the other direction. Here are some other examples. If you had some ammonium nitrate, which is a compound you actually used in a lab back in first year chemistry, where you took 4 different white salts and dissolved them in 4 different containers of water and measured whether the temperature went up or down. And you were talking about the heat or calculating the heat of solution. Ammonium nitrate, if you were to take a tablespoon and dump it in water, you would find that it would gradually dissolve. It would not stay together as a tablespoon of sugar and, ammonium nitrate, and just sit at the bottom of the beaker. It would go from high concentration and distribute itself throughout the water. And in the process, it would also be endothermic. Notice that it is a positive 25.7 kilojoules per mole of ammonium nitrate. This means that the temperature is going to change, that the temperature of registered by a thermometer, or if you were holding the beaker in your hand would feel colder. The temperature would go down as heat flowed from the surroundings into the system. Remember, the temperature would be part of the thermometer would be part of the surroundings. Expansion of a gas into a vacuum. Look at the picture in the margin of 2 spherical glass globes with a valve in between. When the valve is closed and you have gas on one side, sort of the beige colored appearance, and it's no gas on the right side, if you open the valve so that it's parallel to the passageway between the two orbs, you'll notice that the gas distributes itself. It doesn't stay put. So gases expand. That would be the spontaneous direction. And it might be very, very slow. It might be very, very rapid, depending on the temperature. Phase changes. And that also depends upon the temperature. At very cold temperatures, water would spontaneously become a crystalline structure called ice. At a higher temperature, crystalline structure called ice, a solid, would naturally become a liquid. Phase changes can be spontaneous. You would never expect a phase change to be spontaneous. For example, if the temperature was very, very high, above 0 degrees Celsius, and you had water, you would not expect it to spontaneously freeze, or any part of it, for that matter, to freeze. Energy transfer as heat generally goes from hotter to cooler, from wherever the temperature is hottest to wherever the temperature is coldest. And of course, that's one of the parts of the second law of thermodynamics, of the laws of entropy, is that energy gets distributed as well as matter gets distributed. And when we talk about this energy, we have to pay attention to whether the change is positive or negative, endothermic or exothermic. We're also going to have a positive sign and a negative sign when we talk about the distribution of particles or matter. And you might remember from first-year chemistry that a positive entropy means an increase in entropy, an increase in disorder, an increase in the distribution of matter. A negative entropy would actually be an increase in order. If you pick up your messy bedroom, that's a negative entropy as far as the bedroom is concerned. But it would be a positive entropy as far as you were concerned. Now here we have a focus just on the dispersal of energy as it relates to entropy. In a spontaneous process, energy goes from concentrate to dilute, to being more dispersed. And we use the letter S to stand for entropy because the letter E already stands for energy, and we can't use the letter E to stand for heat energy, so we use enthalpy and talk about a delta H. In physics, we often use the letter Q to talk about the quantity of heat. You might remember that we basically have 4 laws of thermodynamics. When the first and second laws of thermodynamics were in place, they realized that technically both laws depended upon an underlying assumption, and that was that heat transfer always goes from hot to cold. If two things are in thermal contact, meaning heat can be transferred, there's no insulating barrier between them, whatever is hottest will cool down, whatever is cooler will warm up until they both reach the same temperature. That became the 0th law of thermodynamics. The first law of thermodynamics we learned a long time ago. Energy is neither created nor destroyed in a chemical reaction. And then the second law has to do with the fact that a spontaneous process is always going to result in an increase of entropy of the universe. So, for example, if you clean up your room, a small part of the universe, your room, is going to show a decrease in entropy, an increase in order. But overall, it's going to cost you some of your order because you're going to dissipate heat and probably exhale some carbon dioxide and gases, and those will gradually spread out throughout the entire universe. If I can remind you, however, do not tell your mom if she asks you to clean up your room, I can't because I don't want to increase the entropy of the universe. That excuse is not valid. The third law of thermodynamics we'll talk about in a little bit. Now, we can define thermodynamics in terms of heat, equation 19.1. The change in entropy, I should say define entropy, is equal to the quantity of heat, that's the letter Q in this case, divided by the absolute temperature in Kelvin. So therefore, the units of entropy will be joules per Kelvin. And that's going to be very important later in this chapter when we get to Gibbs free energy. Now, at the microscopic level, if we wanted to think about this idea of entropy, we can think about energy changes as being in an immediate vicinity, localized, close by, concentrated in the test tube, in the beaker, or whatever, and then gradually over time spreading out and being dispersed, and ultimately, of course, across the entire universe. Again, if you're having a little trouble with self-image or feeling like you're just a nobody, keep in mind, you, by the very fact that you are listening to this scintillating presentation, are changing the entire universe. I hope that makes you feel important. So let's talk a little bit about this dispersal of energy at the microscopic level. Now, look at these 10 pictures at the top of the page. For clarification, each box contains 4 particles. So we have a very, very, very simple system. 4 particles. 1, 2, 3, 4. Each box contains 2 packets of energy, 2 quanta. And they are represented by the beige color, the yellowish color. And if a particle happened to have 2 quanta of energy, you would put a circle around that yellowish color. So in the first picture in the upper left-hand corner, you have particle number 1 with 2 quanta of energy and particles 2, 3, and 4 that don't have any. That is one possible state, one microstate, showing you a configuration of this very simplified system. The next picture to the right, which contains the same particles and the same packets of energy, you'll notice that one particle number 1, has a packet of energy, and particle number 2 has a packet of energy. This is another possible configuration of this simplified state, another microstate. In the third picture, particles 1 and 3 have the packets of energy. In the fourth, particles of 1 and 4 have the packets of energy. In the fifth box, in the upper right, particle number 2 has both packets of energy, and so forth. And when you look at all the possible combinations here, you can see that there are 10 possible microstates for this miniature system, this simplified system of particles and energy. And you can imagine what would happen if we begin to get more and more complicated systems, which of course you're becoming more and more realistic that way. No system is really going to be that simplified. And so imagine, for example, instead of having 2 packets of energy and 4 particles or atoms, we had 2 packets of energy and 6 atoms. And as soon as we do this, notice that we increase the number of microstates substantially up to 21. And of course, as you increase the number of particles and the number of packets, the number of microstates is going to increase exponentially. It's one of the reasons why you can understand that in science, you can never have an exhaustive, 100% complete, total understanding of any system. Scientists need to be a little bit humble and careful about that. Now, this discussion goes on, And one of the people that made this famous a little more than 100 years ago is this rather stern, august-looking gentleman named Ludwig Boltzmann, German, Austrian. And their pictures from that part of Europe, they always seem to be sort of angry. It seemed to be sort of a national disposition for some reason. Very famous. He had this equation engraved on his tombstone. Tells you a little bit about him. Though he did have facial hair and a receding hairline, but sometimes your superior intelligence is not what is necessary in order for you to be a happy and joyful person. In any case, one of his conclusions is that as the number of microstates increases, so does the entropy of the system. What we mean here is that you can actually measure, theoretically, how much disorder is in a system. How much entropy is there in your locker? How much entropy is there in your room? How much entropy is there in a textbook? Technically, we could talk about how much entropy is in any system. And it would be proportional to how many microstates are possible for all the photons and all the atoms that make up that system. In fact, the number is so great that we need to take the natural log of that number. So S is going to be proportional to the natural log of the microstates, W in this case. And so please keep in mind that capital W here does not mean work in this context. Our proportionality constant is the letter K. Pretty common to use the letter K for that type of constant. This is called Boltzmann's constant, and you can see its value is quite small, 10 to the minus 23rd. The same exponent in terms of magnitude of Avogadro's number, 10 to the 23rd, though I don't think there's a connection between the two. Now, not only can energy be distributed, so can matter be distributed. And we've talked about that a little bit. We talked about the gases distributing themselves as much as they possibly can within the confines of the container in which they're trapped, such as figure 19.6, or our atmosphere, if it's released into the atmosphere of our planet. Some of the particles that might be very, very light mass, such as hydrogen, can actually be shed out into the universe because it's not held in place enough by gravity. That's why some of the planets, for example, don't even have an atmosphere because their gravitational pull is not enough to hold the particles of gas in place around the surface of the planet. And it gets shed into outer space if indeed gases are being produced in the crust of that planet. In the bottom of the page, we see a picture of a drop of ink or two, or in this case, perhaps a crystal of potassium permanganate, a purple crystal, being put into a container of liquid. And over time, as the particles move around, as you have the inevitable collisions of water molecules, potassium ions, and permanganate ions, they become evenly distributed. And if it's saturated, you end up having an equilibrium position. Remember, the second law says you're going to spontaneously move towards equilibrium. I should also mention that thermodynamics, then, is extremely mathematical. When you talk about thermodynamics in any depth, you get into the field of statistics. What is the statistical possibility of having this particular microstate or that particular microstate, this configuration or that configuration? And statistics is a very, very complicated and deep mathematical field. I hope you took 1 year or at least a semester of statistics in high school. I think the hardest class that I had in my doctoral program was an advanced course in statistics called Advanced Multivariable Analysis. And here's where we were, instead of looking out at how one variable might be affected by another, how a dependent variable depends upon an independent variable. We do that all the time in high school. We were looking at how maybe 10 or 12 or 20 variables might all affect each other at the same time. So you would need this kind of statistics for very, very complicated systems. And of course, fortunately, now there's computer software that helps with that. But it's interesting to think about the fact, especially in light of conversation today about climate change and about what's the probability of the spread of the COVID virus. And that is that these systems are so incredibly complicated that all of our statistical modeling, a computer model, is embedded with algorithms that reflect our best understanding of statistical probabilities. And our models are woefully inadequate for these complicated systems. And that's part of the problem of giving undue attention to these models. In fact, I've heard it said, somewhat ironically, that no model is correct, but every model can be helpful. No model is true because it can't compensate or take into consideration all possible variables, but they can be helpful. We have to remember that to trust a model is to trust the assumptions that the inventors of that model and the programmers of the computer software that's going to have algorithms embedded in it to run scenarios about that system are only as good as the people that made it. And of course, the people that made it are finite and fallen. So, oftentimes then, when we talk about entropy and when we talk about energy changes, we talk about our system, which might be a test tube or a beaker. It might be a room. It might be something bigger than that. Then we have the surroundings, whatever is surrounding our system. And then ultimately you have the universe. And we can talk about the change in entropy and the change in enthalpy. Now here's where we talk about the third law of thermodynamics. The third law states that a perfect crystal at 0 Kelvin has 0 entropy. That is, S equals 0. This is a logical conclusion. As the temperature gets colder and colder, and you theoretically approach absolute zero, no energy. You can't get there. We've come within a fraction of a millionth of a degree in some very, very micro systems. But as you get closer and closer to absolute zero, the motion of your particles within the crystal go to zero as well. And if you had a perfect crystal with no single atom or ion out of position, no ion or atom that doesn't belong in the crystal, and there is no energy, then you would have this theoretically perfect crystal. And we would call that 0 entropy. And you can see that this third law assumes that that in a sense you can never get to absolute zero because you always need a colder reservoir to dump the last remaining heat into. And if 0 Kelvin is the coldest temperature you can get, you can't get a colder reservoir that you can dump your last little tidbit of heat into. So all substances then have a positive entropy whenever you get above 0 Kelvin. All substances. Now, for the sake of conversation, for the sake of the exchange of information and ideas and theories and calculations and experimental results around the world, we often typically talk about the standard molar entropy. Now, this tells us two things, that this entropy, for the sake of conversation, is going to be per mole, Molar entropy is the entropy per mole for the sake of comparison. And standard has a very similar meaning. It's a benchmark, a common way of expressing things that we agree to use all over the world. Now with gases, we use 0 degrees Celsius, 1 atmosphere of pressure. But in every place else in chemistry, including here, we use 25 degrees Celsius or 298 Kelvin. We use not exactly 1 atmosphere, but 1 bar of pressure. And our solutions are going to be 1 molar in concentration. And so when we make our tables and our charts, they are at these standard values. And you know that because there's that little 0 above the letter S on the right side. S superscript 0. And that 0 does not mean degrees, but means standard conditions. Right there. So, if we can draw some conclusions, large molecules generally have larger entropies than small molecules. And you might say, wait a minute, a large molecule is going to be much more complicated. There's going to be a much more sophisticated arrangement of the atoms that make it up than in a simple molecule. So wouldn't it have less entropy instead of more? And the answer is no, because a large molecule would have lots and lots of microstates, lots and lots of slightly different arrangements of its particles that would be possible than in a small molecule. If all you had, for example, was a diatomic molecule of hydrogen gas, there aren't too many arrangements for those 2 hydrogen atoms. But there are many, many possible arrangements for a much more complicated molecule. And so it would have larger entropy. Molecules with more complex structures have larger entropies. That's something that's very important to remember. Entropies of gases are larger than those of liquids, and entropies of liquids are larger than those of solids. And as obviously a solid, you have a highly ordered crystalline array for almost all solids, except for your amorphous ones like plastics and rubber and some things and glass. But everything else, this crystalline structure, this matrix, this organized pattern or array breaks down and becomes more disordered and random as you go from a liquid into the gaseous state. And so as you go in that direction from solid to liquid to gas, you get a huge increase in entropy, especially as you go from liquid to gas. Now, it's very difficult, obviously, to look at a system, be it what's in a test tube, what's in a beaker, what's in a room, and say it has a certain amount of entropy. What we can do is to talk about how much the entropy has changed. It's the same idea with heat. To look at a test tube or a beaker and room and say how much heat does it have, you'd have to be able to measure the kinetic energy of every single particle in the system. You'd have to measure the entropy of every single particle in the system. But you can measure the change in energy in a system by looking at its change in temperature or a change in state. And you can measure the change in entropy the same way. When we talk about the change in energy, we take the heats of our products minus the heats of our reactants. And this is new, equation 19.3. We do the same thing for the change in entropy. We take the change in entropy of our products minus the change in entropy of our reactants. Where are we going to find our changes in enthalpy, our delta H's? We look them up in charts. Where are we going to find our changes in entropies? We can look them up in charts. And we can also calculate them if we're given sufficient information. So in this particular math problem, we have the two particles of nitrogen monoxide, 2 molecules, and 1 molecule of oxygen. So we have 3 molecules of gases on the left side of the arrow becoming 2 molecules of on the right side of the arrow. That obviously is going to be an increase in order. That's going to be a negative entropy because you're going from 3 particles down to 2 particles. You're reducing the number of possible microstates. And so you would take the entropy of your product, which is nitrogen dioxide, and subtract from it the entropies of your reactants, which are nitrogen monoxide and oxygen. And you would multiply those entropies by the coefficients in the balanced equation, something that some of you forgot to do. You might remember way back when we took a test on this in first year chemistry. Whenever you do your heats of products minus heats of reactants, those heats must be multiplied by the coefficients in the balanced equation. When you look up those values from a table or a chart, or they might be given to you in a problem, in this particular situation, we get a negative 146.7 joules per Kelvin mole. The joules per Kelvin is our unit for entropy. The mole gives us at standard conditions. And it's negative because it's a decrease in entropy. You're going backwards. And here's some more examples of this, and you're going to get some in your homework. And I'd like to pause for a minute and interject an interesting thought. However you want to describe the moment that the universe sprang into existence, and it's typically called the Big Bang, which back in 1949 was actually a sarcastic term used by a famous astronomer, Fred Hoyle, as he was mocking the idea that the universe had a beginning, because he knew that that meant the universe had a beginner, one who started it. What would be the entropy? Well, if the universe, and we know this right now that the universe is expanding, that means that the matter in the universe, as well as the energy, is becoming more and more distributed. And if it's becoming more and more distributed, entropy is increasing. That is the second law of thermodynamics. So if you go back in time, the universe didn't have as much entropy. It had more order, which means if you go back to the first moment, the moment when God said, "Let there be," you have the most order, the most organization, the most information, from a human point of view, an infinite amount of order and design and information and logic. And we're reminded of John 1:1. In the beginning was the Word, capital W-O-R-D, which in Greek is the Logos, referring to Jesus, the author of the logic and the meaning and the rationality and the order in creation. We can use this idea as we continue that the changes in entropy of the universe equals the changes in entropy of the system plus the changes of entropy in the surroundings. So, for example, if you're cleaning up your locker or your bedroom, the change in entropy of the system might actually go down because you're cleaning it up. But as a result, the surroundings, which would be you, and whatever heat that you generate, that's going to go up. And overall, the change in entropy of the universe has to go up. That's the second law. We can also look at smaller systems in the same way. And again, we add up all of the all of the entropies of our products, and we subtract all of the entropies of the reactants. And you can see here this symbol, sigma n S sub aught. Sigma n s aught, where aught is the little zero. It's a superscript, it's not a sub. And so the sigma is the Greek letter for summation of, Greek letter S. The n represents the coefficient from the balanced equation for that particular product or reactant. S is your entropy, and the little aught or circle is standard conditions. At the bottom of the page, there's all kinds of ways we can manipulate this equation. We can look for the change in entropy of the surroundings. And what this basically means is you're going to have to read each problem on a homework or a test very carefully to know whether you're talking about the system, the surroundings, or the universe. We usually don't talk about the universe that much. And if we're talking about the system, paying attention to what's a product and what's a reactant. Also, please remember the sign usage. Just like positive delta H is endothermic, negative delta H is exothermic, positive delta S is an increase in entropy and disorder, negative delta S is a decrease in entropy or disorder. And a lot of students mix this up because a decrease in entropy is the same thing as an increase in order. And these signs are down here at the bottom of this page. And just like we had a chart in first year chemistry that talked about the different values of delta H and delta S, here's that chart again. So let me give you 4 illustrations. Number 1, let's think of combustion or an explosion. Is it exothermic? Absolutely, because it releases energy when you burn something or combust something or blow something up. The heat is dissipated, so your delta H is going to be negative, exothermic. Heat is exiting. What about your particles? What about the entropy? Well, both your entropy and your particles are being thrown out into the surroundings. So you're going to have an increase in disorder. And so your system will always be spontaneous because both your delta H and your delta S are working together. Now let's look at number 4. Let's think about photosynthesis. Photosynthesis is absorbing solar energy. So it is gaining heat energy. So you have a positive delta H. And in the process, you are making complicated molecules like glucose from very simple molecules like carbon dioxide and water. And as a result, your entropy then is negative because you're creating more order. This system is never spontaneous. It always requires work being done by the sun. Now, in number 2, this kind of system would only be spontaneous at a lower temperature. Can liquid turn into a solid? Think about water freezing. It would be exothermic because you have to lose heat in order to freeze. But in the process, you're becoming more ordered, more highly arranged in the crystalline structure of ice. So this would only be spontaneous at low temperature. And think about water evaporating. That would be only spontaneous at a higher temperature, because for liquid to become a gas, you have to absorb heat, endothermic. And as a result, you're distributing your particles into the atmosphere, so it's an increase in entropy. And so what we need then is an equation that can put together the delta H and the delta S and weigh one factor off against the other. And that's going to be Gibbs free energy, which we're coming to in a minute. And this page contains some examples of those 4 types that I just finished talking about. So here's Gibbs free energy. Gibbs free energy, named after a guy named Gibb, basically puts these two observations together. It puts the delta H together and the delta S together. And the way we normally look at it is at the bottom of page 19.5. And here your delta G, your change in Gibbs free energy, is your delta H in conjunction with subtracting your delta S. And of course, the entropy factor depends upon the absolute temperature T. And so here's your third set of signs. You've got to know positive and negative for delta H, positive and negative for delta S. T is always going to be positive because it can never be lower than 0. It's Kelvin. And so delta H can be positive or negative. Delta G. So when delta G is negative, that tells me that this system, this combination of heat and entropy, is spontaneous. When delta G is positive, it means the combination of the effects of the delta H and the effects of the delta S is non-spontaneous. And that you would be expected to memorize. And again, we can evaluate combustion and freezing and evaporation and photosynthesis in light of Gibbs free energy and show mathematically why they would be spontaneous or not, depending on the temperature, and in some cases not depending on the temperature at all. And we did that in first year chemistry. And we'll stop right there.